Hello everyone, welcome back to my channel. In this video, we are going to learn the concept that is a second law of thermodynamics. Before going to this second law of thermodynamics, we have to know what is meant by a reversible process. Reversible process. The process which can be retraced in opposite direction such that the working substance can pass through a perfectly same state as that of direct process, that we can call it as a reversible process. And simply we can define it as the process which can retrace in opposite direction, that we can call it as a reversible process. And we are going to observe a different example for this reversible process, and those are, the first one is fusion of ice. The first one is the fusion of ice. So we can convert the water into ice and ice to water. Therefore, this one we are considered as a reversible process. And the second one is vaporization of water. And this one is one of the example for this reversible process. And the third one is gradual compression and expansion of spring. And this is about the examples of reversible process. The process which can be retraced in opposite direction, that we can call it as a reversible process. In this case, the working substance can passes through exactly same state as it passes through the direct process, and even in a reverse process, that we can call it as a reversible process. And next one is irreversible process. The process. So here the statement for this one is the process which cannot be retraced in opposite direction, that we can call it as irreversible process. The process cannot be retraced in opposite direction, that we can call it as irreversible process. And we are going to observe the example for the irreversible process is rusting of iron. So one of the example for irreversible process. So in this case, we can't convert the rusted iron to the normal iron. Therefore, this one we are considered as a example for irreversible process. And diffusion of gases. Diffusion of gases. And so if you consider the two different two different gas. So if we diffuse those two different gas, we can't separate after that. So that is therefore we are considered the diffusion of a gas is one of the example for irreversible process. And third one is dissolving soap with water. And this is also one of the example for irreversible process. And this is about reversible and irreversible process. And nextly, Carnot's heat engine. So firstly we have to know what is meant by a heat engine. Heat engine is an idealized engine which converts heat to mechanical work. Heat engine is an idealized engine which converts heat to mechanical work. Which can convert heat to mechanical work. And this is about a heat engine. So here we have to know that the work done by the system. Is same in direct process, is same as the work done on the system in a reverse process. So the work done by the system in a direct process is same as that of the work done on the system in reverse direction. So even we are going to observe in direct process, the heat absorbed in a direct process is same as that of heat given out in a reverse process. So based on this, the example we are considered refrigerator. It works on the principle of the Carnot's heat engine. So here, this heat engine was explained by Carnot. Therefore, we are going to observe the Carnot's heat engine. Carnot heat engine consists of the first one is a source, and the second one is a cylinder, and the third one is a sink, and the fourth one is a stand. So these are the parameters or the different materials we are going to observe in the Carnot's heat engine. So here there is a diagram for this Carnot's heat engine. Let us consider this one as a source, and this represents a stand, and this represents a sink. And this one as a cylinder. And this is a source, and this is a stand, and this one is a sink, and this one is a cylinder. So here, let us consider one by one. The first one is a source. A source is a hot body of infinite thermal capacity. It is a hot body of infinite thermal capacity. It maintains a constant temperature, high constant temperature, that is T1. It maintains the high constant temperature that can be represented by and T1, and it can supply any amount of heat energy to that working substance. It can supply any amount of supply any amount of heat energy to the working substance, that we can call it as a source. And the next one is a cylinder. A cylinder is this one is a cylinder. A cylinder is which is having a perfectly conducting base or bottom. We can say the perfectly conducting base or bottom, and a perfectly non-conducting walls. These are the perfectly non-conducting walls with the perfectly non-conducting piston, and the 1 mole of a gas is taken in that. 1 mole of a gas is taken in the cylinder as a working substance. Is that right? So here the perfectly conducting base and the perfectly non-conducting walls with the perfectly non-conducting piston, and the 1 mole of the gas is taken, ideal gas is taken in a cylinder as a working substance. Is that right? And that is about the cylinder. And the next one is a sink. A sink is a cold body of infinitely thermal capacity. Here, and it is in temperature. It maintains a constant temperature that can be represented by a T2. It maintains a constant temperature that can be represented by a T2, and it can absorb any amount of heat energy. Here we are going to observe in case of a source, it can supply any amount of heat energy. Right? And here a sink, it can absorb any amount of heat energy. And this is about the Carnot's heat engine. Here. And the next concept is thermal efficiency. Thermal efficiency. Here the thermal efficiency that can be represented by beta, which is equal to the ratio of external work done to the ratio of external work done to the amount of heat energy absorbed by the working substance from the source, that we can call it as a thermal efficiency. So in this work done divided by absorbed heat. The work done divided by absorbed heat. In a sense, the ratio of external work done to the amount of heat energy absorbed by the working substance from the source, that we can call it as a thermal efficiency. Here the thermal efficiency that can be represented by eta is equal to work done that can be written as a W divided by absorbed heat that can be represented by Q1. Is that right? So here the work done can also written as Q1 minus of Q2 divided by Q1. Therefore, this can also written as eta which is equal to 1 minus of Q2 divided by Q1. So we can also represent this one as 1 minus of T2 divided by T1, because we are maintaining a temperature T1 and T2, a T1 for the source and the T2 for the sink, and amount of heat energy absorbed by the source that can be represented by Q1 at a constant temperature T1, and the amount of heat energy given to that sink that can be represented by a Q2 at a constant temperature that can be represented by a T2. This is about a thermal efficiency.